Hi class, today we are going to talk about chapter 9.1, the beginning of chapter 9, which is all about linear transformations. So this is linear transformations, definitions, and properties. This is basically a review of what we covered in chapter 3.1 about linear transformations, but then we're also going to incorporate all of the other things that we've learned throughout this semester about linear definitions. This is really a review section. I don't suggest that you skip it by any means because we're kind of compiling everything that we've talked about for linear transformations into one place. So onto-ness, one-to-one-ness, surjective and bijective transformations is another name for those. The kernel, things like that, right? So it's a lot of definitions, a lot of theorems, a lot of review, but it's good because we'll have them all in one place. So we're going to be looking at these things under the lens of vector spaces rather than the real space or R3 or R2x2 or what have you, like we were before in chapter 3. Now that we know about vector spaces, we can talk about linear transformations in terms of vector spaces. So a transformation from one vector space to another vector space. Okay. So let's review our definition of a linear transformation. So I try to incorporate linear transformations throughout every chapter so that they don't get lost in us, right? So there's a very specific way to define and to prove that something is a linear transformation. So let's say that we have two vector spaces, V and W. Then a linear transformation from V to W is a linear transformation that is defined by T if for every two vectors that we have in the vector space V, which we'll call V1 and V2, and a scalar C for our function T that satisfies the following, that if we add two vectors together and take their transformation, it's the same as taking the transformation of the individual vectors and then adding them together. That if we take a transformation of a scalar multiple of a vector, it's the same thing as having a scalar multiple of the transformation of a vector. Okay, so these are the two properties that we have that we need to satisfy to be a linear transformation. Again, this should not be new. We have seen these several times throughout the course so far. So here, however, we're calling V the domain and W a codomain. So before we're using the standard definition of vectors where we had a column of numbers. So this might have been something like R3 and this would be R2, right? So here we have vector spaces, so they can be matrices, they can be functions, they can be smooth functions, they can be all sorts of different objects now, right? So let's bring this to another theorem. T from V to W is a linear transformation if and only if the property of a scalar multiple of a vector plus a scalar multiple of another multiple is the scalar multiple of the individual transformations, right? So basically, if we take the transformation of a linear combination, we can just basically apply both of these properties at once, right? So again, you guys have seen me say this before as well. Okay, and this has to be true for every set of vectors, every pair of vectors in our vector space V, and for a pair of scalar multiples such that this is how we're defining, such that we're taking a transformation of a linear combination in this fashion. All right. Definition: if V is a vector in our vector space V, then T of V is the image of V under the transformation T. Okay. If S is a subspace of V, then the transformation of this subspace is a subspace of W. Okay, so again, remember T is a transformation from V to W. So if we have a subspace of V, the transformation or the image of that subspace is a subspace of W. Okay. So consisting of all images of the elements of S. Okay, so all of the vectors that are in S, their transformation is inside of this transformation of S, which is a subspace of W. Okay. The range of T, right, or the codomain, which we notate by range of T, is the subset of W consisting of all the images of the elements of V. Okay, so it's very similar to what we have here. Here, this is just for a subspace. The range is the set of all images of V into W. Okay, that's the range, which we call T of V, right? The transformation of the entire vector space. The kernel of T, called curve T, is the set of elements V and V such that when we take the transformation, we don't get the zero vector, we get the zero vector for the vector space W. So remember, sometimes our zero vectors are not all zeros, right? So whatever the image of our zero vector looks like in W, the kernel of T is all the vectors in V that go to that zero vector when they are transformed by T. Okay. The kernel of T is a vector, sorry, it's a subspace of V. So remember, kernel of T, it's the set of vectors in V, right? It's the set of elements in our vector space V, right? So the kernel of T is a subspace of V itself. And the range of T is going to equal all of W, okay? So, next theorem. So let T be the linear transformation from V to W. Then the kernel of T is a subspace of V, which we stated above. Okay. If S is a subspace of V, then the transformation of S is a subspace of W. So that was part of what we had above here. It's two of them actually. Okay. So what does that mean is that linear transformations preserve linear combinations. Okay. We know that because of this, right? This small theorem here. Transformations preserve linear combinations. So the image of a full subspace is also going to be a subspace. Okay. So that's the reasoning for it. Okay. So definition. Let T be a linear transformation from vector space V to vector space W. Then T is one-to-one if for every vector W in W, there's at most one V in V such that the image of V is equal to W. Okay. So again, as I said before, hopefully you guys reviewed chapter 3.1 video because I'm not including any of the pictures that I had in that video here. But we had a lot of images and diagrams. We had, so this is like chapter 3.1 heavy, right? So 3.1.1 you can call it, right? This is where we're not having a lot of images. We're really formulaic for this approach because we're going to use all this stuff throughout the next couple of videos, right? So if you want to see visual representations of these things explained a little bit more in depth, go to the chapter 3.1 video where we discuss linear transformations at a much more basic level, right? So remember what it means to be one-to-one? It means that every vector in V goes to only one vector in, has its own vector, in W. Okay, so every vector in W has only one or none vectors in V that go to it. Okay, there will never be two vectors in V that map to a single W. Okay, that's one-to-one. T is onto if for every vector we have in W, there is at least one V in our vector space V such that the imaging of that vector goes to W. So what that means too is that everything in W gets mapped to by something, right? There's a full coverage of W, our vector space W, right? So there could be multiple vectors in V that go to a single W, but all of the W's have to be mapped to. That's what it means to be onto, okay? So another theorem, let T of V to W be a linear transformation. then t is 1-to-1 if and only if v goes to the 0 vector in W has only the trivial solution where v is the 0 vector in V. Okay, so what this means is the only way for this to work, to be 1-to-1, is if the only vector that goes to the 0 vector in W is the 0 vector from V. Okay. Theorem. Let T be a linear transformation. Okay. So suppose that V is a set of vectors, V1, V2 up to Vm, is a subset of the vector space V. Okay, so again, notice that the V's are different here, and the W's are different here, right? So the curse of W is a set of vectors that's a subset, not a subspace, just a subset, just a collection of vectors of W. And a transformation of any one of these vectors maps to one of these vectors, right? So transformation of V1 maps to W1. Transformation of V2 maps to W2, so forth for all the vectors. So if W, this set, is a set of linearly independent vectors, then so does these vectors as well. Okay. Theorem. If T from V to W be a linear transformation with V and W finite dimensional, okay, so these are finite dimensional vector spaces, then the dimension of V is equal to, this is basically the rank nullity theorem, right? The dimension of the kernel of T, the things that go to 0, plus the dimension of the range of T. So in the rank nullity, this would be that the dimension of our domain is the same as the dimension of the null space plus the dimension of the rank, but since we have linear transformations, null space is the kernel and the rank is the range, right? So that's our relationship here. Okay. Theorem. Let T be a linear transformation from V to W. Okay. V and W both finite dimensional. If T is onto, then the dimension of V is going to be greater than or equal to the dimension of W, right? Because if you have a bigger space here, it can easily map to everything in W. However, if your space here is smaller than W, you cannot cover the entire range, right? The entire codomain space. If T is 1-to-1, then the dimension of V is less than or equal to W, right? So everything here can go somewhere into W. It doesn't necessarily have to cover the entire thing. Okay. So now let's get into examples. So all of those theorems and definitions were things that we have seen before. The only difference is that now we're talking about them in terms of vector space instead of Rn and Rm like we did in chapter 3.1. So now we're going to, I'll spend more time on the examples because again, those definitions and theorems, those were review to me. In my eyes, they're things that you've seen before. They shouldn't be hard to pick up if you are familiar with how these linear transformations work, right? So let's spend a little bit more time on the examples. We'll walk through those a little bit more slowly, but obviously this is going to be a fairly short video, right? Okay, so let T be a linear transformation from R 2x2 to P2, okay? Satisfying the following. Yeah, so if we take a matrix from 2x2, that's 1, -2, -1, 3, we get out the second degree polynomial x squared minus x plus 3. Okay, so we don't have, this is not a general term, a b, c, d, but we're saying that, hey, if you transform this specific vector in R 2x2, then you will get out this specific output in P2. Okay. Same here. Under the same transformation, if I put in this specific vector V, I guess for this domain space, I will get out this specific vector W for this codomain space. Okay. So it wants us to find T of 7, 2, -1, 7. So now this is the problem, right? So if you have reviewed chapter 3.1 or you just remember linear transformations in general, generally they give us a generalized, hey, if you plug in this thing, this is your transformation matrix A, and when you transform by this transformation matrix A, when you multiply it times your input vector, you will get out this output, right? We don't have the general form of the transformation here, okay? So what we have to do then is we have to, let's go back, use one of these several definitions that we went over, okay? So if we go through here, there's a few things that we can use, okay? So a lot of these definitions, like for instance, this one is just talking about the the transformation itself, right? What happens when you take something and you send it out. Here you can transform a whole space, transforming a single vector. This is what goes to 0, things like that, right? And as we come down, we're talking about transforming subspaces. We're talking about one-to-one and onto-ness quite a bit. We're talking about 0 vectors, right? And then we're talking about basically having a set of vectors that is one-to-one and onto between themselves, right? And then we're talking about the dimension. Now, none of that really helps here. We're not talking about a 0 vector. We're not talking about one-to-one and onto here. We're not talking about the range. We are, but not specifically because we have a very specific set of vectors. So what I want to do is I want to figure out what I can use, right? So it's actually the only one that I skipped over way at the beginning, which is this property, okay? A linear combination. The transformation of a linear combination allows me to separate this into the outputs times the scalar multiples that I had for my linear combinations. So I have inputs, okay? I have outputs for those inputs, okay? But I don't have the linear combination for the vector that I want. So that's what I'm going to do. Okay? So I have two inputs. I need to write this as a linear combination of these two things, and then I can write this in terms of the two outputs. So I'm going to use that linear combination form that we had. Okay, so if I can write this as a linear combination of these two, then I can use the output t of v1, which is this, and the output of t of v2, which is this, and I can multiply them by the scalar multiples that I needed to write this as a linear combination of these two to form my answer. Okay, so we need c1 times v1 and c2 times v2 to be v3, where v3 is this vector. Okay, so I need a scalar multiple times my v1, which I'll call this, and a scalar multiple of this to equal this. And so this is very standard, right? We know how to solve this. This is actually like from day one, the kind of things that we were learning how to do. So t of c1 times this linear combination here is the same thing as t of this vector here, right? So I write this up as an augmented vector, okay? So as long as in the way that I do this, right? So if this is my first entry, second entry, third entry, fourth entry, I need to make sure that's true for these as well, right? So my column vectors are 1, -2, -1, 3. So I'm zigzagging this way because that's kind of the standard way that we do that, right? So when I make this augmented matrix, I'm turning these matrices into column vectors, right? 1, -2, -1, 3. 1, -2, -1, 3. So I turn them to column vectors. I solve this augmented matrix. I would use an inverse here, but it's not square, so I can't use inverses. But I can just use my standard reduced row echelon form in my calculator, and it tells me that 3 and 2 are the solutions. Now, if I came up with no solution, right, then there'd be no solution to this problem. But thankfully here, my coefficients are 3 and 2. So the transformation of 3 times that first vector plus 2 times the second vector gives me the resultant vector that I wanted. So since now that I know it's 3 and 2, I can separate this into its parts. The transformation of 3 times the first vector plus the transformation of 2 times the second vector still will get me the result that I want. Okay, I can slowly, obviously I'm doing this step by step, right? So I can pull out these constant terms to the outside of the transformation, and then I can replace my transformations with their results, right? I know the transformation of this is x squared minus x plus 3, and the transformation of this vector is 3x squared plus 4x minus 1. So then I just have to simplify this to a single vector in P2, because that's my codomain. So I get out 9x squared plus 5x plus 7, right? So I did that without knowing the general form of my transformation, right? Or my transformation matrix. Right. Next example. So we want to describe the kernel and range of the linear transformation from the smooth functions from an interval of 0 to 1 to P2, right? Polynomials of second degree with the following, right? So if we transform a function from the smooth functions from 0 to 1, we will get f of 0, that function evaluated at 0, times x squared plus that function evaluated at 1, right? So remember, these are going to be constants. If I evaluate a function at a point, I get a constant out, right? So this is basically some constant times x squared plus some constant, right? For my function to be in the kernel, okay, so it's got to be a function, obviously, because that's what is my domain, right? It's the smooth functions, things that are differentiable from 0 to 1, differentiable and continuous. So it has to be a function in kernel of, in order to be a function in the kernel of this transformation, the things from here that undergo this transformation that end up in the 0 for the polynomial space, right? So a good question is, what's a 0 for the polynomial space? Well, the 0 vector in polynomial space is just 0, right? Because these are basically, once you evaluate them, regular numbers. So 0 plus a polynomial gives you that same polynomial out, right? So we just have to think about what it means to be a 0 vector. So for P2, the 0 vector is the standard just scalar value of 0, right? So in order to be in the kernel space, this implies that the transformation of this function in the kernel undergoes this transformation and will give you out 0, right? So I want to know all the things that when they undergo this transformation, we get 0, okay? So again, note that f of 0 and f of 1 are scalar values here, right? Because you're evaluating a polynomial at a point, so you get out a scalar value. Therefore, f of 0, okay, is going to be equal to f1 if I want this to be 0, okay, which is 0, right? So if f of 0 is 0, I get 0 times x squared, which leaves me f1 equaling 0. So I need all of these things, both of these scalars here, to be 0 in order for it to be in the kernel. Therefore, the kernel of T is the set of functions, okay, such that when you plug in 0 is the same thing as when you plug in 1, getting you 0. So that's the first part. The next part is to find the range of T. So we want to find what all of the things look like when they get sent somewhere. So there's a pretty good hint here for what the outputs look like. So since we have f of 0 and f of 1 being scalar values, we can say that f of 0 is a and f of 1 is b, right? Those are real values. So therefore, the range of T are the set of things, right? So inputs here is going to be functions of x in this case, or polynomials, I should say, such that the polynomial looks like ax squared plus b, right? So those are all the things in the range because our range are full of polynomials. Our domain is full of functions, right? So functions in the domain, polynomials in the codomain in the range. So we can simplify this by saying that the range is just the span of the basis vectors that can create any polynomial of this form, which is any linear combination of x squared and a scalar value 1. Okay, so our range is the span of x squared and 1. Okay, so for this next example, we want to determine if the transformation from P2 to P3 given by plugging in a function f and multiplying it by x is 1-to-1 or onto. And again, obviously this function here is a polynomial function, not just a regular function. So v in P2 has the form of f of x equals ax squared plus bx plus c. And obviously when we transform a vector, we're just taking this general form and we're multiplying it by x, right? So we're going to get ax cubed plus bx squared plus cx. So remember, to show that something is 1-to-1 or onto, generally what we do for 1-to-1 is we show that something is linearly independent, although that's going to be a little difficult here. And for onto, we got to show that it maps onto the entire space, right? That the entire range gets mapped to. For 1-to-1, right, if we go back to our definitions here, okay. So we had some definitions about dimensions, but we can't use these for onto and 1-to-1 because these theorems say that if we are already onto or already 1-to-1, then these relationships between the dimensions are true, right? The converse doesn't hold. We can't say that since this is true, we're onto 1 or that we're onto. It doesn't work that way. Okay. Here we're using the nullity rank theorem, so that doesn't have anything to do with 1-to-1. This is not 1-to-1. Well, it is, but it's not. This is generally what we would use for 1-to-1, and this is generally what we use for 1-to-1 or onto as well, right? So we're kind of going to go with these definitions, right? Generally, again, 1-to-1, we talk about the zero vectors, okay? So let's go ahead and use those for our example. Okay. So for 1-to-1, this implies that T is 1-to-1 if and only if the image of a vector from P2 is going to be the zero vector for P3. And that's true if it's only the trivial solution, which means that that input vector was the zero vector from P2. Okay. Now the lucky thing here is that the zero vector for P2 and the zero vector for P3 are the same thing. It's just the scalar 0, right? So remember that a zero vector has to satisfy this property. 0 plus v is equal to v plus 0 is equal to v. So the only way that works with any polynomial is if the zero vector is 0, right? So the zero vector for here is the scalar 0. Okay. So note that the 0 for P2 is the same as the zero vector for P3, which is just 0. And that's true basically for all polynomials. And that the kernel is the set of the zero vector, right? So the kernel here is the zero vector, which means that here A, B, and C all have to be 0. Okay. So the transformation of f of x to be 0, which is what it means to transform the zero vector, right, is going to be the zero vector for P3, right? So that's the only way for this to work. So remember, we're showing this property, okay, that if I plug something in here and to get out 0, so plugging something in here to get out 0, which is the zero vector for W, in this case P3, implies that I had to have plugged in the zero vector in the first place, right? Because there's nothing else I can plug in here that looks like this to get out all zeros, right? So for ax squared plus bx plus c to be turned into this and get 0 out, the only way for that to work is if I have a and b and c being 0. Right? Since the zero vector here is as follows. So if I transform the zero vector, that means that I'm multiplying 0 times x, because that's what my transformation is, which will give me out 0, which is this. And that's the only way to get 0 out in P3 by plugging in the zero vector of P2. Okay. Therefore, the kernel of T is the zero vector of P2. That's all the things that go to the zero vector here is the zero vector of my domain, right? So that means that I'm one-to-one, because the definition for one-to-one for a transformation is that the only way to get the 0 vector out for your range is to plug in the 0 vector for your domain, and that's true. Everything that goes to the 0 vector in the range, right, is the 0 vector in the domain. So I'm one-to-one. Okay. And then now we have to look at onto. Okay. So therefore T is one-to-one. So in order to decide whether or not it's onto, we know that when we transform a vector, it's going to look like this: ax cubed plus bx squared plus cx. And the range of T, in this case, is going to be the span of the basis vectors for creating this, which is any linear combination of x cubed, any linear combination of x squared with x itself. Okay, and that is not equal to P3. Now we can use the dimensions, because the dimension of P3 is 4, and the span that I have for the range is a dimension of 3. And since the dimensions are not equal, there's no way for everything here to cover a dimension of 4. This is a bigger space than this is, so there's no way for this to cover that, right? So if we go back to the theorem that we can use for that, that's going to be those dimension theorems here, right? So if it was onto, the dimension would have to be larger than the dimension of V would have to be equal to or larger than the other one, and that doesn't hold, right? And so since this is not true, this is not true. Okay. Now we can't use it the other way where we say since this is true, that this is true. That we cannot do, but we can say that since this is not holding, that this is not holding either. Okay. So we can use the negative of the converse, right? That's how we would say that in math. Let's go all the way down here. Okay. So these things are not the same since their dimensions are not the same. Now, if these dimensions were the same as this was 4 and this was 4, we would say it covered. Or if this was a dimension of 5 and this was a dimension of 4, we could then say that it covered as well. Okay, but that's not true. All right, and that's it. So I'm sure this was a little bit more difficult than normal because it's not just all vectors. We're having functions and things like that we're dealing with. But again, if you have not already, please go and revisit chapter 3.1 and then maybe watch this one more time after watching that video one more time.